Welcome to India's number one and largest IIT student community with 70,000 plus students on board. If you are preparing for the IIT Madras BS degree qualifier, then you are in the right place because this is the best one-shot statistics video enough to crack your qualifier statistics. In this revision series, we will cover all the important statistics concepts, shortcuts, problem-solving techniques and exam-oriented questions that you need for the qualifier. Whether you are revising at the last minute or just strengthening your fundamentals, this series is designed to maximize your preparation. Before we begin, we're excited to announce that we have officially launched our IIT Madras BS Qualifier Crash Course. If you want structured preparation with expert guidance, this is the perfect opportunity to boost your qualifier score. Along with the crash course, if you are looking for one-to-one live class mentorship, 24/7 doubt support, strategy session, structured preparation, and previous year paper solving in live classes, you can join India's number one IIT Madras BS degree qualifier coaching to the link provided in the pinned comment below. Our coaching program has consistently delivered 90 to 100% selection rates with top-notch faculty having a minimum of 10 years of industry experience. Our team owns 13 nuanced patents in AI, ML, and IoT, and we also serve as guest lecturer at IIT, where we teach advanced topics like LLM, RAG, and AI agents. So grab your notebook, stay focused till the very end, and let's begin the best one-shot statistics video to help you crack your IIT Madras BS qualifier. At first, let us see the introduction to statistics. What is statistics? Statistics is the art of learning from data. Statistics is the art of learning from data. That is, we'll be summarizing data and we'll be taking some inferences. Inferences means insights. We'll be taking from insights from data and we'll be learning from the data. First, it was about collecting and summarizing data. Then it became about inference means drawing some conclusions, insights from the data. Now, with lots of data around us, it is the art of learning from it. Statistics is the art of learning from data. Okay. So, according to Sheldon Ross, statistics is the art of learning from data. You are concerned with collection of data, subsequent description, summarizing. Description means summarizing, and their analysis with which often leads to drawing of conclusion. Okay. So you're learning from data, summarizing it, and you're drawing some conclusions. Okay. There are two main branches of statistics. Statistics has two main branches, which are descriptive statistics and inferential statistics. Okay. Descriptive statistics and inferential statistics. Descriptive statistics is concerned with description and summarization of data. Note this, descriptive statistics is only concerned with description and summarization of data. There will be no conclusions here. No conclusions or no insights drawn here. Okay, there will be no conclusion, no insights. It just summarizes the data. Like if you are having a the descriptive statistics will only give you their mean, median, mode, who got the highest mark, what is the average marks of all the students, and what is the middle value of that marks. Like that only you will be getting. It's just summarizing. So this is how the pattern is. Okay. But inferential statistics, on the other hand, it concerned with drawing conclusions from data. So, for example, with the same marks data, if one particular student is failing in from the first grade, okay, from first grade, second grade also he is failing, third grade also he is failing in maths, like this means, then it will be more likely that he will be also failing the fourth grade maths. So using these three data, you will be going to draw a conclusion that in the fourth grade also he will be failing in maths. So this is what we call as the inferential statistics, concerned with drawing conclusions from data. Okay, so inferences involve uncertainty and possibility of chance. See, description just summarizes. The descriptive statistics just summarizes the data, but inferential is concerned with drawing conclusions, but those conclusions also uncertain. Uncertain means it can happen or cannot happen. See, for example, we can use the weather prediction for this. See, it may rain today. In the weather report, in the news, they will always say it may rain today because According to their data, according to their inferences, it can rain, but there are some other factors. Sometimes when the wind blow high, when the wind is blowing high, the clouds will get scattered and it may not rain. That we don't predict how the clouds move. So inferences will always involve uncertainty. It may happen. There is a chance of happening. That is what the inferential conclusion is. Okay. So before knowing statistics, you have to first study probability. Okay. So see here, let us see now what is a sample of one population. The complete collection of all elements that we are interested in is called as the population. So population is the group of all the peoples or objects under study. See, group of all people or objects under study. Okay, all people are all objects under study. Okay, but sample is the subset of the population that is studied in detail. See, population is containing all people or object, but sample is just a subset of population. It will contain some of the elements of the population. See here, if this is the population, then sample will be one of each. See, one of each color. So this is what we call it as a sample. Most of the time we'll be taking the sample values randomly. Okay. So a sample is a smaller part of the population and we want it to be as representative as possible. See here, for example, we had a question in GA, right? So where we had to study about where the education minister wants to know about the placement opportunities throughout all the engineering institutes in India. But this is the population. The population is all the placement opportunities in all the engineering institutes in India. But the researcher took only five IITMs, five IIT colleges. Okay, five IIT based colleges. Is this a best representative of the population? Is this sample the best representative of the population? No, right? Because IITM is different. IIT is different from all the engineering colleges. All the engineering colleges include many colleges other than IIT too. So this is not a good sample. Okay, a good sample should be representative of the population as possible. See here, a good sample should represent the population well. If the sample misses some important groups, example, see here, this is a group. Here we are having different colors: orange, blue, some skin color, and then I'm having white here, and there's yellow here. Okay, but see here, there is no yellow present here. I'm having yellow here, but I'm not taking yellow here. So which means that the sample is not representative. Okay, so in this one I'm including yellow, so this becomes representative. So this is how we pick out population and sample. Okay, so why do we need the concept of population and sample? Collecting data on every element of a population is often time consuming. See, take the same example itself. The education minister wants to study the placement opportunities in all the colleges of all the engineering colleges of India. This is possible and this is impossible, and it takes more time than we think, than we predict, right? So what we are doing, we are randomly selecting engineering colleges from all over the country. We are randomly selecting uh, um, the engineering institute all over the country. So we'll be having a sample which represents the population, so that we do not have to work on that large data. Okay, so see here the population, for example, let us say we are having some 1 lakhs engineering institutes in India. We cannot go and study about the research, do research about the uh, all the engineering institutes in India, as it will take time, and it is very costly, and it is not practical. Okay, so from this population we'll be taking some from this population we will be taking some samples, which will be I'm taking some engineering institutes from all over the different states. Okay, so from Tamil Nadu I'm taking some, from Kerala I'm taking some, from Maharashtra I'm taking some, like that. And if let's say I'm having some 10,000 samples, okay, 10,000 samples randomly selected all over the states of India. Okay, so this is a best representative of a population. So I can extend the inferences I have drawn from this sample to this population. Okay, so see, for example, percentage of all students in India who has passed class 12 and study engineering. Okay, this is a great population. We cannot directly work on the population, so we have to find some subset. And prices of all houses in Tamil Nadu. This is also very high example and very high population. Total sales of all cars in India in 2019. This is a very very heavy data. Okay, and age distribution of people who visit a city mall in a particular month. There will be 10,000 more than lakhs of people visiting a city mall in a particular month. Okay, so for these examples we will be using the population and sample concept. So we study a well chosen representative sample to make reliable inferences about the entire population. See, we don't always study everyone. We study a good sample and use statistics and learn and draw conclusions about the whole. Okay. The next one is understanding data. Understanding data is the heart of statistics. Understanding data is the heart of statistics. So what is data? Data is just facts and figures collected. Okay, it can also be some facts, or it can also be in numbers. Okay, so data is just facts and figures collected. For example, comments on a video, photos, likes or clicks, purchase online. It can be numbers, it can be words, it can be images, comments, clicks, or anything we create online. So example of data in daily life means we are always surrounded by data. Everything we see, everything we hear, everything we feel comes under data. So we all collect data all the time. For example, household accounts. See here, at date at this date I have brought this item, and the amount I spent was this. At this date I have put petrol for my vehicle, and the amount is this. And at this date I have spent this many amount for snacks. Okay, so this is also data. Every click, key, press, search, like or share we do online also generates data. Data does not say anything. It is a fact. Okay, so it is just a fact. We are using this data. We are processing this data to extract information and answer question. Okay, so there is so much data that are being generated every second. Our job is to turn it into a meaningful information. Okay, so why do we need to collect data? Why do we need to collect data? The main reason is we want to know about the characteristics of the groups. So for example, you are studying about some people. You you have to collect data about them, right? For example, if you're doing some work research on the ancient Egyptian peoples, how they built the pyramid, like that, then you have to collect the data about them to have some insights about them, right? So we'll be collecting the data. While we'll be collecting the data to know about the characteristics of that particular group of people. So if you have to know about a place, you have to collect the data. If you have to know about a thing, for example, you are going to purchase something in Flipkart. So what you will do, you'll not go and directly order one. You will be doing some research about that, right? You'll check all the reviews and star rating it is getting, and all the YouTube reviews it had. So this is also a part of collecting data. This is how we are collecting information about that particular thing. Okay, so we collect data so that we can answer our questions. So we are collecting the data about that particular thing I want to buy from Flipkart to know whether it is worth or not, whether it is worth my money or not. So we collect data so that we can answer our questions. Okay, so for example, we can keep cricket data. We collect cricket data to answer questions like this: who has played the highest number of matches, who has the highest batting average, who has taken the highest number of wickets, how has a player's performance has been over time, is there a difference in performance at home versus away match. To answer all these questions, we need to have the data of that particular players. Okay, so now we have to know our data, classify the data, and we have to use our data. So the data should be in the structured format to get more insights from the data. So data can be structured or unstructured. Okay, so unstructured data will be like paragraph, something like that. Paragraphs, likes, comments, shares, images, and the phrases. These things will all come under the unstructured data. And in structured data, it will be organized in a data table like this. It will be organized in a data table like this. Okay, so the data is organized in a data table, and the columns we call them as variables, and rows we call them as cases or observations. Okay, and rows we will call them as cases or observation. So look at any data set you see, you will see numbers, text, and both. See here, name is a text, but marks is a number. Again, board is a text and marks is a number. So we will be having a combination of both text and numbers. So data is not all the same, it has different types, and we must classify it to understand the data better. Okay, so see here, there are two types of data. One is categorical data, other name is qualitative variables, it and the next other one is numerical data, which is also called as quantitative variable. Okay, so categorical data will be just the names or the names that can be ordered. Okay, see here, data is classified into categorical data and numerical data. That categorical data is again split into nominal and ordinal, and the numerical data is again split into continuous and discrete. Okay, so see here, this categorical data is the one which can be just names or the names that can be ordered. Okay, so see here, these are just names. You cannot do any mathematical computations using these names. Or okay, see, you can only find mode for the categorical data. You can find only mode for the categorical data. But otherwise, the numerical data, they are not names. They are just the numerical values. They are just the numerical values that can be added, subtracted, multiplied, divide, or any other computations, any other arithmetic computations you can think of. Okay. So in that we have two classifiers, right? Discrete, continuous. So discrete is the numerical thing that can be counted. That can be counted, and continuous is the numerical thing that can be measured. Okay, discrete is a thing that can be counted, and continuous is a thing that can be measured. Okay, so see here, now let's deep dive into those two topics. Categorical data, this identifies a group members, places observations to categories or groups. See here, gender, male, female. You cannot do any mathematical computations. They are just names. Okay, board, state board, ICSE, CBSE. These are just names. You cannot do any mathematical computations. Blood group. Again, O positive, A negative, B positive, A positive, O negative. These are just names. You cannot do any mathematical computation. Role. Batsman, all-rounder, etc. So these are also just names. You cannot do any mathematical computation. Remember, jersey number, mobile number, zip code, and all these things are also come under categorical data because they are just unique numbers. Okay, you cannot add two jersey numbers and get the mean of those jersey numbers. Jersey number is a is a alternative for a name of a player, right? See, whenever you see the jersey number 7, you know it is Dhoni. Okay, and whenever you see the jersey number 18, you know it is Kohli, right? So these are just some representatives for that players. Okay, it is not a real mathematical value which was counted or measured. They are just the representatives for that particular player. Okay, they are just the representative for that particular players. So jersey number is also categorical. It is a qualitative variable. And mobile number is also a categorical data because you will be not adding to mobile number and subtracting and finding the difference between them. Mobile number is just a unique number provided to each person so that we can call them. Okay, it is not a thing which is counted or measured. Okay, so mobile number is also a categorical variable. Okay, now let us see the numerical data. The numerical data represents the numerical properties. Okay, so the numbers on which the arithmetic operation will make sense. So numerical data is the numbers on which the arithmetic operations make sense. See, marks, you can add all the marks of the students and find their average. Height, you can find the average height of a person in the class. And weight, and using this weight you can calculate the BMI and you can say whether the person is overweight, underweight, normal or obese. So temperature, using this temperature you can find the average temperature and use it to calculate how the weather will be tomorrow. Blood pressure, and all these things are come under numerical data. Matches played, batting average, wickets taken, highest score, bowling average, runs scored, all these types come under numerical data. Okay, so the numerical data is divided into two types, which is discrete and continuous. Discrete is the thing that can be counted, for example matches played, and continuous is the thing that can be measured, that is batting average. Okay, so see here, whenever we will be getting units like this, it will come under numerical data. Okay, so the measurement unit matters. Numerical data should always have a unit. The unit must be consistent across all the observation. So height, it should be in centimeters. Weight, it should be in kilograms. Temperature should be in degree Fahrenheit or Celsius. Anything. Or in Kelvin also. Marks should be in marks. Okay. Matches played should be matches only. Wickets taken should be wickets only. So same, it should be consistent across the data. Same variable, same unit, and always. For example, if you have the height 1 in centimeter and if you have the height 2 in meter, the data is inconsistent here. You have to convert either one of them to one unit. So you have to convert the meter into centimeter so that you will have h1 also in centimeter and h2 also in centimeter. Now you will be having the same unit and you can consistently perform your observation. Okay, now let us see what is the time series and cross-sectional data. See, time series data is the data on the same variable collected over time. Okay, see here, see the date is fixed here. Okay, the date is changing here, the time is changing here. The data on the same variable collected over time, see, tracks how a variable changes over time. So see here, the time is changing here and while the variable is fixed. Okay, the time is changing here, changes over time while the variable is fixed. Okay, so in the time series data, the time will change while the area is fixed. Time changed, area fixed. Okay, in cross sectional data, area will be changing, area will be changing while time is fixed. Okay, so in time series data, time will be changing and area will be fixed. And in cross sectional data, time is fixed and area will be changing. Data and many variables collected at the same point in time. So compares same point in time means time is fixed. Compares many units at one time. Okay, so student data or hospital data, these are all will be at one time. What was the student doing? It is see the marks data. The exam was conducted on same day for all the students, but we are collecting for different students, right? This is what we call as the cross sectional data. So what you must to do with any data set, we have to classify whether it is numerical or categorical, and if it is numerical we have to identify the unit of measurement and check consistency across all the observation. Check, that is, you have to check whether they are present in the same units, and determine if the data is cross sectional or time sectional. So doing this, you will be understanding the data better. Okay, so understanding the type of data will help us to lead to the right summary. Okay, so see here, we know what a data is. Now we have a tidy data set, that is, we are organizing it into columns and cases and observations in a row. Then each case has a value for each variable, and we can classify the variables as categorical or numerical. So the next step is we have to learn from the data. We need to learn to summarize it, right? So the summarization can be graphical or numerical. So to do the numerical summaries, we must know the scale of measurement of each variable. Okay. So examples of variables in data set. See, in student data, we will be having name, gender, board marks. And in hospital data, we will be having height, gender, blood group, weight. And in cricket data, we will be having player, role, matches played, batting average, jersey number. Here, the categorical variables are name, gender, and board. The numerical variable is marks. And in hospital data, the categorical variables are gender and blood group, while the numerical variables are height and weight. Okay, in the cricket data, the categorical variables are player, role, jersey number, while the numerical data is matches played and batting average. Okay, so some variables are number, some are just text. So some numbers have meaning, some numbers don't. See, for example, matches played, batting average have meaning. You can do some computations with that. But jersey number is just a jersey number. You cannot do anything with that. Okay, some numbers do not have meaning. So the data is broadly classified to two types. We saw this, categorical and numerical. So anything which can be measured comes under measured or counted comes under numerical data. The other data which can be just named, or the names that can be ordered, comes under categorical data. Okay, so the numerical data has two types, which is discrete, which contains the numbers that can be data that can be counted, and continuous, which contains the data that can be measured. Okay, so for continuous, the example will be height, weight, batting average, etc. And for discrete, the example will be matches played, number of matches played, number of wickets taken, number of students who failed in maths, like that. Okay, so important, we have to always check the unit of numerical data. It must be consistent. Okay, we have to always ensure this. Okay, and there are four scales of measurement. The first one is nominal scale. Nominal scales mean the data will just consist of labels and name, no order. For example, students name, gender, board, they cannot be ordered. You cannot order males first and females first, or females first or males first, right? They are just a representative of their sex. Okay, so these things cannot be ordered. Okay, and see, jersey number is also it may seems like a number to you, but jersey number is just a representative for that particular player, so it is a nominal scale. Okay, so maybe when gender is numerically coded, we will be writing male is equal to 0, female is equal to 1, or male is equal to 1 or female is equal to 0. Both codes are valid. You have to check whether the question is using which of these two codes. Okay. So nominal scale is just the naming categories without implying order. Okay. Whereas ordinal scale is just the improvement of nominal scale where order or rank is meaningful. For example, see the customer service rating where 4 customers have given a rating here. So for customer 1 has given the rating as excellent, while the customer 2 has given as good, while the customer 3 has given as bad, and 4 can be good. So we can arrange them from best to worst, right? So we can arrange them like this. Excellent will come first, and good will come next. Again good will come next, and bad will go to the down. So I'm going from best to worst. Okay. So ordinal scale is named or categories that can be ordered. For example, if the student 1 has got second rank, and student 2 has got fourth rank, and student 3 has gotten third rank, and 4 has gotten first rank, then you can arrange them like this, right? First, second, third, fourth. So this is what we call as the ordinal scale. Okay. And the other one is interval scale. The order is meaningful, differences are meaningful, and but no true zero. Okay. But no true zero means you can go beyond 0. See, 0 means, see, uh, 0 should mean empty, but here it will not mean empty. So there is no true 0 here. See, when I get temperature 0, I will think that there will be, I will not think that there is no temperature. I will think that there is 0 degrees, 0 degree Fahrenheit here, 0 degree Celsius here. Okay. So the 0 is not exactly empty here. Okay, the 0 is not exactly empty here, and you can also go beyond 0. See, I can also have minus 10 values, minus 10 degrees Celsius. So 0 here, 0 degree Celsius is not equal to absence of temperature. So interval scale is order plus meaningful and differences, but you will not have true 0. That is, you can go beyond 0 to the negative values. Okay. But in ratio scale, order is meaningful, differences are meaningful, true 0 also exist. See, for the height, if you get 0, 0 means there is no height for him. Okay. Absence of height is there, and you cannot represent the height as minus 20 centimeter. You cannot go beyond 0, and 0 means empty here. So the ratio scale is order plus meaningful differences plus true 0. Okay. Now let us move on to describing categorical data. Okay. Now let's move on to describing categorical data, that is frequency distribution. Now let us see how we will be describing the categorical data based on frequency distribution. For example, we are having some simple data where data is equal to, categories are A, B, C, D, and data our observations is A, B, C, A, D, A, B, C, D, C. Okay, so I'm listing all the categories here, and I'm representing the count of each category has tally marks. So I've got A once, twice, thrice, 4 times. So I'm putting 4 tally marks, and I'm writing the frequency count as 4. Okay. And see here, then I'm going to count B. I got B only 2 times. So I'm putting 2 tally marks, and I'm writing the frequency count as 2. And let's see the C here. Let's see the C here. I'm getting C once and twice. So I'm putting 2 tally marks, and I'm writing the frequency count as 2. Okay. Then D also I'm getting only twice. So I'm putting 2 tally marks and I'm writing the frequency count as 2 here. Okay, and I'm getting the total as 10. See here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So see here, I got the frequency count of each category. A has come 4 times, B has come 2 times, C has come 2 times, and D has come 2 times. So this is the frequency count of each category. Okay, so what are all the steps to construct a frequency table? List the distinct values. That is, you have to list all the categories first. For each observation, place a tally mark in that particular category. Okay. So count the number of tallies. That is the frequency. Okay. See, count the number of tallies. That is the frequency. See the example 2. There are 15 observations. A, B, C, A, D, A, B, D, C, A, B, C, D, A, where the tally marks are, let us count 1 here, sorry, let us count A here, 1, 2, 3, 4, 5, 6. There are 6 here. Then the tally marks will be like this, 1, 2, 3, 4, 5, 6. So the frequency is 6 here. Okay, and let us count B here, 1, 2, 3. 3 times I have got it. So the tally marks will be 1, 2, 3 and the frequency is 3. Okay, let's see C here, 1, 2, 3. So 3, again 3. D is also for 3 times, again 3. Okay, so see here, in this categories, in this all these 15 observations, A is occurring the most here. A is the most frequent thing here. Okay, so we'll be using a frequency table to represent the categorical variables. Okay, the categorical variables. And we should also know how to do frequency table in Google Sheets, but this is not required for your this qualifier, because they will be not asking questions from Google Sheets. You just have to know so that you can work better. Okay, and see the graphical displays of categorical data. For categorical data, will be the most two common graphical displays will be pie charts and bar charts. Okay, so what is a pie chart? A pie chart is a circle divided into pieces or wedges. Each wedge shows the share of a category. So it is best for showing proportions of a whole. That is, when you have to show the shares or part or how they are being divided, then you will be using a pie chart. Okay, share of a pie. Okay, and how to construct a pie chart? We have to draw a circle and convert the relative frequency to degree. You know how we calculate the relative frequency? Relative frequency is equal to frequency divided by total number of observations. So frequency divided by total number of observation. Here the frequency is 4 and the total number of observation is 10. So 4 divided by 10 will give me 0.40. And here 2 divided by 10 will give me 0.2. And 2 divided by 10 again give me 0.2. And this 2 divided by 10 will again give me 0.2. So when we add up all the relative frequencies, we must get 1. Okay. The sum of all the relative frequencies should be 1. Only if it is 1, then the data is consistent and the relative frequencies are correct. If you do not get 1, then your answer is probably wrong. Okay. So now we have to convert the relative frequencies to degrees. Degrees is equal to relative frequencies into 360. Relative frequencies into 360. Okay. See here, I have to multiply 40 into 360. Okay, so which will be 144 degree. And again I have to multiply 0.20 into 360, which is 72. Again 0.20 into 360, which is 72. 0.20 into 360, which is 72. So after finding all the degrees, you have to add them up all and you must get 360. Only then the degree you have found is correct. Okay, so we have to mark the angle for each category, and then you will be shading each wedge with different colors to represent different categories. Okay, so see, this is how the pie chart will be. The data of the people is given. Sometimes they will be giving the percentage. The percentage can also be used to represent, draw a pie chart. Otherwise, you have to find the degree. Degree is equal to relative frequency into 360, where relative frequency is equal to frequency divided by total number of observations. Okay. So let us see what a bar chart is. A bar chart displays distant values on the horizontal axis. Horizontal axis. Okay. So the height of each bar represents the frequency. This is best for comparing frequencies across categories. So pie chart is best for showing the proportions or how much a particular category will occupy, while bar chart is used for comparing the frequencies across categories. Okay. So when should we use pie chart? Pie chart should be used when the goal is to show how parts make up the whole, and we should use bar chart when the goal is to compare categories. Okay. So let us see the best practices for pie chart and bar chart. Okay, so what is the purpose? Before creating a table or a graph, we should ask ourselves, what do I want to know from this data? Okay, what do I want to know from this data? So if the purpose is to just count and list categories, we can simply use the frequency table. Okay, if the purpose is to compare counts across categories, we can just use the bar chart. And if the purpose is to show the share or proportion of each category, then we will be using pie chart. Okay, so use pie chart when we want to show the parts of a whole. For example, regional distribution of 100 students, and we have to use a bar chart when we want to compare categories. Compare categories frequencies. Okay, so number of students from each region. Okay, so the pie chart is best for showing proportions and bar chart is best for comparing counts. Okay, so when should we use a table? We should use a table when we have more categories and we want exact numbers and details. Okay, so let us see how we should label our charts. Okay, we should give a clear and meaningful title. Okay, add a subtitle if needed, and we should show the percentages values on the slices. Okay, like this, and keep colors distinct and easy to read. That the colors must be so obvious. You should not give the other shades of blue to this one. You should be making it more different and in context to make it easy to read. And do not explode all the slices. Explode only if essential. Okay, so there should be legend, there should be percentage of slices in this to make it valid. Okay, and for a bar chart, you must all have a clear title, and the label should be there, x-axis and y-axis. Okay, and we should start the y-axis from 0. So you have to use consistent and clear colors. Okay, so right display plus clear labels will give us the clear message. Okay, so now let us see area principle and misleading graphs. Okay. So how to display the categorical data honestly? Okay. So the big idea is the area principle is the area occupied by the part of the graph should correspond to the amount of data is represent. That is, the graph should tell the true story of the data. So what the area principle means, area shown in the graph should be proportional to the data value. Decoration should not distort meaning. Equal width bars plus proper baseline plus clear scale help honest display. See here, this cannot be a bar chart. Okay, this cannot be a bar chart because this is very bottles on tops of label boxes, and there is no proper baseline here. Shapes and size are inconsistent and it is hard to compare values, right? So we should not be using decorative graphics like this in our data representation. So how we should represent this is what a good representative will look like. See, the baseline should start at 0, and we should have distinct bars for each category, and you have to have the units and the labels here. Okay, so the right chart obeys the area principle. So we have to be careful about truncated graph. A truncated graph will be a misleading graph. Okay, a truncated graph is when the baseline of a bar chart does not start at 0. The truncated graph is when the baseline of the bar chart does not start at 0. See, this chart is starting at 75, not 0. So this is a misleading truncated graph. Okay, this is a misleading truncated graph. You have to start at 0 no matter how big the value is. Okay, so why truncate is a problem? It will be exaggerating the differences and can mislead the audience, and it will cause the loss of honest visual information, and it violates the good practice and principle and area principle. Okay, so if you must change the y-axis, you have to show a clear y-axis break like this. Okay, and tell the reader that the axis does not start from 0. We should not never hide the break. Okay, so the best practices or rules will be, you have to keep the baseline at 0 for bar charts. Okay, keep the baseline at 0 for the bar charts, and you have to use equal width bars, and you have to show the scales clearly. Okay, and we have to label the categories clearly, and we have to avoid unnecessary decoration, and we have to preserve the data integrity, and if axis is altered, you have to mention it like this. Okay, so summarizing categorical data. Now we are going to be introduced to measures of central tendency. What we call as the measure of central tendency, it is a single value that lies at the center, or the most typical, or is most typical for a data set. So for the types of variable like categorical or nominal, the measures of central tendency will be mode. Most common category will be mode. Okay, while median is calculated only for ordinal data. Mode can be calculated for nominal and ordinal, but median is calculated for only ordinal data. Okay, and for numerical data, you can have the all these things, mean, median, and mode. Okay, so in under categorical variable, mode is possible for nominal and ordinal, but median is only possible for ordinal data, while mean, median, mode is possible for both interval and ratio data. Okay, so mode means the most common category. That is, mode is the category with the highest frequency. See here. Here I am building a frequency table for those categories. See, I'm having A 1, 2, 3, 4, 5, 6 times. Okay, 1, 2, 3, 4, 5, 6 times. So I'm having the count as 6, while B is less than 6. B is less than A. See here, 1, 2, 3, 4. I'm having only 4 times. C is 1, 2, 3. I'm having only 3 times. And D is 2. 1, 2. Okay, so only 2 times, where A has the highest frequency. So A is the mode. Okay, the category with the highest value count is A. Therefore, A is the mode. Okay, so what are all the key points about mode? The key point is the mode is applicable to both nominal and ordinal data, and it can also be used for the numerical data. Okay, there can be one mode, unimodal, more than one mode, bimodal or multimodal, and or there can be no mode also. Okay, so it shows the most frequently occurring category, and it is easy to understand and interpret, and it is not affected by the outliers. Okay, it is not affected by the outliers. And see the median. The median means the middle category, which is only possible for ordinal data ordinal data and the numerical data. Okay, so the median is the middle category when the data are arranged in order. Okay, for example, in ordinal data you can arrange them like this, right? Poor, fair. Poor is less than, fair is less than, good is less than, very good is less than, excellent, right? So let us see how we calculate median here. So we are going to count each categories and represent it in a frequency table like this, and we are going to do a cumulative count. Cumulative count means this 2 will be written here, then 2 plus 2 is 4, 4 plus 5 9, 9 plus 1 is 10, 10 plus 2 is 12. Okay, this is what we call as a cumulative count. Okay, so here n is equal to 12, right? So n is equal to 12 means the middle positions are 6th and 7th. Okay, the middle positions are 6th and 7th. So 6, see, 6 7th falls under this category. The value 6 7 will fall under this category, right? So this both fall under the same category. So the median is good. Okay, the median is good. Can you understand? We are doing the cumulative count, and see here 6 and 7 will fall under this category. So the median is equal to good. Okay, so the key points about median is it is applicable only to ordinal data and numerical data, and the categories are arranged in order. See, we have to arrange them in order and we have to use cumulative frequencies. If n is odd, then the median value is at n plus 1 by 2th position, and if the n is even, we will be taking the average of the values at n by 2 and n by 2 plus 1. See, we will be taking the average of the values at n by 2th and n by 2th plus 1 positions where the category will both fall. Okay, so it is less affected by extreme categories and it gives the middle position of the data. Okay, so let us see mode versus median. Mode is the most frequent category where median is the middle category, and data type is it is for both nominal and ordinal. It is for only ordinal. Okay, it is for only ordinal. And how to find? We will be using using the most popular or common category, and we will be using the most middle category. Okay, and is it affected by extremities? No, it is not affected by the outliers. Okay, so the best practice is to always create a frequency table first. Okay, so for mode we have to pick the category with the highest count. For median you have to ensure the categories are in order, and we have to clearly state whether the mode is bimodal, unimodal, etc., and interpret the result and the concept of data. Okay, then see here, now let us move into describing numerical data, that is using single variable. Okay, so see here, numerical data we had two types, discrete and continuous, where discrete is the count of something that takes separate values. For example, 68, 75, 43, 52 marks of students. Okay, and continuous data is something where it represents the measurement of something, can take any value in a range. For example, it is weights 68.5, 75.3, 43.2. So let us say that the discrete data will always be some whole numbers, while the continuous will have a combination of both whole numbers and continuous decimal numbers. Okay, so we will summarize both discrete and continuous data. For single values, we will be using small data, and for class intervals, we will be using group data method. Okay. So for describing numerical data, the agenda is define the frequency tables, graphical summaries, numerical summaries, and measures. Okay. So frequency table for discrete values, small number of values. See, number of people in a household where 50 people were survived. Okay, so the distant values are 1, 2, 3, 4, 5. Okay, so now I am going to take the distant values in one column, which is x. Okay, then I am going to count how many ones has occurred. 1, 2. So 2 times. 2 has occurred 1, 2, 3. 3 times. So 3 tally marks. So 3 has occurred 1, 2, 3, 1, 2, 3, 4, 5. So it is 5. Okay, and 4 has acquired 4 times and 5 has acquired 1 time, so total I'm getting 15. So now I'm going to calculate the relative frequency, which is relative frequency is equal to frequency divided by total number of observations, that is 2 divided by 15 is 0.133, 3 divided by 15 is 0.2, and 5 divided by 15 is 0.33, and 4 divided by 15 is 0.267, and 1 divided by 15 is 0.067. So adding all these relative frequencies, I should get 1. Then only it will be a correct value. Okay. So the bar chart will be used to represent the frequencies. So key point is each distant value should be a category. Each distant value, that is 1, 2, 3, 4, 5 should be a category. Construct a frequency table as same as for the categorical data. No special methods for numerical data. We have to construct the bar chart as we constructed for the categorical data. Okay. And the bar chart shows the counts. Bar chart shows the counts of each distant values. Okay, so the order is meaningful here since it is a numerical data. You cannot keep bar chart like this 1, 4, 5, 3, 2. It should be like this only 1, 2, 3, 4, 5. Since it is a numerical data, the order should be preserved while representing the bar chart. Okay. Now let us see the frequency table for the grouped data. See, here we are having 50 students and we cannot write the distant value of each student like this, right? See, 30, 31, 32, 33, up to 50 I cannot, up to 100 I cannot write like this, right? So what we will be using? We will be using some class intervals, okay? So we will be using some class intervals. The class should, number of classes should be usually 5 to 20, and each observation must belongs to one class and only one class. See, you cannot keep 40 here and 40 here also, then it will duplicate the same data. You have to keep 40 in either one of these two classes. Okay, so it is a good practice to use equal class width. Equal class width means, see here, here you will be having 10 values, here also you will be having 10 values, here also you will be having 10 values. So this is what we call as the class width, and it is good to keep a equal class width. Okay, so we have found the class intervals like this, and we can now mark the tally marks. See, 35 is come under this category. So 1 I'm having, then see, then I am having this 36 which will come under this category. So 2, and then I am having 32 will come under this category. So 3. Okay, so I am having 3. And 30 also come under this category. So 4. Okay, and see here, then 40 to 50. This is how I represent it. I'm going to find the tally marks, and then I'll be having the frequencies. Then I divide the frequency by total number of observations to get the relative frequency, and this relative frequency should add up to 1. So this is how we put the frequency table for grouped data. There are some terms for group data, which is the lower class limit. This is what we call as the lower class limit, and this is what we call as the upper class limit. Okay, and the class width is UCL minus LCL, which is 40 minus 30. Okay, which is 10. The class width is 10. Okay, class mark, that is LCL plus UCL divided by 2, that is 30 plus 40 divided by 2, which is 35. 70 by 2, which is 35. So the class mark is 35. And convention, the class interval contains its left end but not the right end. So 30 to 40 means you have to include 30 in this interval but not 40. So 40 is included in the next interval, and 50 is not included in this interval, and 50 will be included in this interval. 60 is not included in this interval, and 60 will be included in this interval. 70 is not included in this interval, and 70 will be included in this interval. 80 will not be included in this interval, and 80 will be included in this interval. So this is what we call as the convention. So 30 to 40 means 30 is less than or equal to x less than 40. Not 40 will be included in the same class. Okay. And for grouped data, we will be using histogram. For single value, we will be using the bar chart, and for grouped data, we will be using the histograms. Okay, so how do we draw an histogram? How do we draw an histogram? We will be obtain the frequency distribution table and we'll draw the horizontal axis with class intervals same as the bar chart, but we'll be not having the unique categories or unique values here. We will be representing the class intervals here. Okay, and the histogram will be continuous. This image is wrong. Histogram will be continuous. It will not be having any gaps. Okay, the bars will touch each other. So it will be like this. It will be continuous where the bars is touching each other. Okay, this is how the histogram will be. This image is wrong. Okay, so bars will touch each other. And let us see what is a stem and leaf plot. Okay, so for example, if you are having values like 15, 22, 29, 36, 31, 23, 45, 10, 25 and 14, we will be splitting each observation into stem and leaf. Okay, so stem will be all the digit except the rightmost digit. Okay, so this is the right, we'll skipping the rightmost digit and we will be taking all the numbers other than the rightmost digit. So see, if you having 291, you will be taking the this one alone, this one you will be skipping this one alone, and this will be your stem. 29 will be your stem and 1 will be your leaf. Okay, so similarly, if you have 399, 39, the rightmost digit will be your leaf. See, the rightmost digit will be the leaf and all the digits except the rightmost digit will be your stem. Okay, so in 15, 5 is the leaf and 1 is the stem. And in 22, 2 is the leaf and 2 is the stem. And 29, 9 is the leaf and 2 is the stem. So in the stem and leaf plot, you have to arrange all the leaves in the ascending order. Okay, write stems from smallest to largest. This also should be in smallest to largest in a vertical column, and write each leaf to the right of the vertical line, and we have to arrange all the leaves in the ascending order. Okay, now let us move on to describing numerical data. So the best way to summarize numerical data is using numerical summaries. So there are two types of numerical summaries. One is measures of central tendency and one is measure of dispersion. So measure of central tendency will tell us where the data is concentrated. What is the most typical value? So mean is the most common, and sometimes we can also use median or mode. Okay. And measures of dispersion will tell us how the data is spread out, how much variability is there in the data. Okay, how much variability is there in the data. Like that, it will represent the dispersion. Okay, mean. First let us see mean. Mean is equal to sum of all the observations divided by the number of observations. Okay, the sum of all observations divided by the number of all observations. So sample mean will be represented using the x bar, which is equal to x1 plus x2 plus x3 plus xn divided by n, where n is the sample size. Small n is the sample size and capital N is the population size, where population mean is represented by using mu, where mu is equal to capital X1 plus capital X2 plus capital X3 up to capital Xn divided by capital N, where capital N is the population size. For example, the data is given like this: 4, 3, 1, 2, 5, where n is equal to 5. So x bar will be 4 plus 3 plus 1 plus 2 plus 5, which is 15 divided by 5, which is equal to 3. So mean is also called as average. Okay, so understand this: small n denotes the sample size and population n denotes the, capital N denotes the population size. Okay, so let us see how we calculate mean for small data sets. See, there are 7 data sets: 2, 12, 5, 7, 6 plus 7, then 3. So that n is equal to 7. So how we will be calculating mean? X bar is equal to sum of all observations divided by total number of observations. Okay, sum of all observations divided by total number of observations. So 2 plus 12 plus 5 plus 7 plus 6 plus 7 plus 3 divided by 7 is 42 divided by 7, which is 6. Okay, but see, There is another method for calculating mean for data using frequencies. We'll be also calculating the mean for the data using frequencies. Okay, so see if the number of people 1 is repeated twice. Okay, so you will be doing 2 into 1. Okay, and you have the same value 2 twice, then you will be taking 2 into 3, 6. Okay, if the value 3 is repeated 5 times, then you will be taking the frequency f of x will be f into x will be 15. Okay, and if you got the fourth value, four number of peoples 4 times, then you will be getting 4 into 4, 16. Okay, and if you have the number of people 5 one time, then you will be having the f into x value will be 1 into 5, that is 5. Okay, so your total frequency is 15, and the product of the frequency and number of people is 44. So the formula for finding the mean using frequencies is x bar is equal to summation I is equal to 1 to n fi xi. So fi xi means I have to add all these things. Summation I is equal to 1 to n fi xi means I have to add all these things. 2 plus 6 plus 15 plus 16 plus 5, which is 44. Okay, divided by summation fi. Summation fi means sum of all the frequencies. Okay, so sum of all the frequency means 2 plus 3 plus 5 plus 4 plus 1. So 44 divided by 15 is equal to 2.93. So 2.93 is the mean for the number of people in the household for 15 people. Okay, and we also find the mean for grouped data, that is continuous data, in the same way. Okay, so in this one we multiplied with the number of people, but in this class interval grouped data, that continuous data, you will be multiplying it with the midpoint. Okay, your midpoint will be the xi, frequency will be the fi, and you will be multiplying with the midpoint. How we calculate the midpoint? We will calculate the midpoint like this: 30 plus 40, that is LCL plus UCL divided by 2 will give you the midpoint, okay. So 30 plus 40 divided by 2 is 35, and 40 plus 50 divided by 2 is 45, and 60 plus 50 divided by 2 is 55, 60 plus 70 divided by 2 is 65, 70 plus 80 divided by 2 is 75, and 80 plus 90 divided by 2 is 85. Okay, so now we got the midpoints and we have the frequencies here. Okay, and frequencies here. Now we have to multiply the midpoints and the frequencies. 35 into 3 is 105, 45 into 6 is 270, 55 into 18 is 919, 65 into 17 is 11,105, and 75 into 4 is 300, 85 into 2 is 170. So you will be taking the sum of all the frequencies and sum of all the fi and xi, fi into xi. So this is 50 and this is 2940. So the formula is x bar is equal to summation I is equal to 1 to n fi xi divided by summation fi. So x bar is equal to 2940 divided by 50, which is 58.8. Okay. So this is an approximation since we are using class midpoints, not the exact values. Okay, the mean for the grouped data will be approximations because we are not using the exact values, we are just using the midpoints here. Okay, so let us see how mean changes when we transform the data. Let us see how the mean will change when we transform the data. When you add a constant to every observation, see for original data, the mean was 59, and then I'm adding a constant c is equal to 5 to each value. Then the new data will also have the mean plus 5. Okay, mean plus 5. The new mean will be old mean plus that constant c. Okay, so you have to remember this. For mean, if you had a constant to all the observation, then the new mean will be equal to old mean plus that constant. Okay, and if you multiply each observation by constant, you will be again getting new mean is equal to the new mean will be the old mean multiplied by that particular constant. Okay, so if a if the observations are multiplied by some constant called 10, and the new mean will also be the value that we got after multiplying the old mean by 10. Okay, so now let's move to measures of central tendency. Measures of central tendency means we will be finding the center of the data set. So whenever we are coming to a center, we will be using the median. The median of the data set is the number that divides the data into a bottom 50% and top 50%. See the definition here. The median of the data set is the middle value in the ordered list. Okay. So how to find the median? So remember this, whenever you are asked to find the median, you have to compulsorily arrange the data in the increasing order. You have to compulsorily arrange the data in the increasing order. Let n is equal to the number of observations, and if n is odd, then the median value will be the value in the n plus 1 by 2th position, and if n is even, then the median will be mean of the n by 2th and n by 2 plus 1th observations. For example, here the n is equal to 5. So the n is equal to 5. So the median will be the value at 5 plus 1 by 2th position, which is 6 by 2, which is third. The median will be the value at the third position. So this is what under the third position. So median is equal to 3. And if the median is even, then we will be having the mean of n by 2th and n by 2 plus 1th observation, that is 6 by 2th and 6 by 2 plus 1th observations average. Okay, so 6 by 2th means third position and this one is fourth position. So we will be taking the mean of the values in the third and fourth position. So the median will be x3 plus x4 divided by 2. Okay, now let's see an example. So now let's see an example here. The data is given here, and we have ordered them as in ascending order. Here the n is 10. So I'll be doing n by 2, that is 10 by 2, which is 5, fifth position, and n by 2 plus 1, which is 5 plus 1, 6, sixth position. So 1, 2, 3, 4, 5, 6. So I will be taking the average of these two numbers, 61 plus 66 divided by 2, which is 127 divided by 2, which is 63.5. So the median is 63.5. This is how we do the median computation. And now let us also see the effect of transformation on median. So we are going to add a constant c to each observation, and the new median is equal to old median plus c. The same rule we did for the mean. New median will be equal to old median plus c. And if you are going to multiply each observation by a constant k, then new median will be equal to old median into k. New median will be equal to old median into k. So mean changes a lot due to the outlier, but median will stay the same. So mean is affected by outliers, but median is not affected by outliers. Okay, so mean is affected by outliers, but median is not affected by the outliers. Okay, now let us see what is a mode. Mode is the most frequently occurring value in a data set, right? Mode is the most frequently occurring value in a data set. So how do we find mode? We find the value that appears most of the time. So how do we do that? We will be finding the frequency of each values, and a data set can have multiple modes, right? So if a data set can have multiple nodes, and if there is no value which is repeated, so that it means that the data set has no modes. Okay, the data set has no modes. So see the example here. Here 7 occurs twice. Okay, so mode is 7. Here also the 7 occurs twice. No other numbers are repeated. So 7 occurs twice. So the mode is 7. Here none of them is being repeated. All are distant. Okay, so there is no mode. So mode is also not sensitive to outliers. See, only mean is affected by outliers. Median and mode are not affected by outliers. Okay, so effect of transformation on mode. Okay, so similarly, when we add a constant c to each observation, new mode will be equal to old mode plus c. Okay, so if the old data will be having mode is equal to 68 and we are going to add 5 to each observation, then for the new data, the new mode will be 73, 68 plus 5, 73. Okay, and when we multiply each observation by a constant, the new mode is equal to old mode into k, that constant. Okay, so for all the three categories, mean, median, and mode, whenever you add a constant, the new mean, median, or mode will also be incremented by that particular constant. And when you multiply each observation by a constant k, that the particular mean, median, mode will also be multiplied by that particular constant. Okay, and another one thing you have to remember is a mean is affected by outliers, while mode and median are not affected by outliers. Okay, so now we saw what is measures of central tendency. What are the measures of central tendency? They are mean, median, and mode. Now we are going to we are going to know about the measures of dispersion, that is how spread out the data is. Okay, so why do we need them? Why do we need the measures of dispersion? Okay, see, we saw the measures of central tendency, which are mean, median, and mode, which describe the center of the data, while the measures of dispersion describe how much the data varies around the center. Okay, the measures of dispersion describe how much the data varies around the center. For example, we are having a data set A, no variation, and B, wide variation. See, data is 33333. The mean will be 3, mode will be 3, and median will be 3. Here it is 1 2 3 4 5. That is, it is 3 3. The mean is 3. See, 1 plus 2 plus 3 plus 4 plus 5 will be 15. 15 divided by 5 will be 3. And the median, the middle value is also 3. And you cannot calculate any mode because there is no repeated values. Same mean and median, but they are clearly different. See here, same mean and median, but they are clearly different. So we do not know the difference here. See here, the values are different, but we are getting the same mean and median. So the mean and median is failing to capture the difference in this values, if difference in this data values. So we are using dispersion measures to capture this difference. Okay, so we will be using dispersion measures to capture this difference. Okay, so let us see range. The range of the data set is the difference between its smallest and largest value. The range of the data set is the difference between its smallest and largest value, and the range is equal to maximum minus minimum. Okay, so the range will be equal to maximum minus minimum, and since range is maximum minus minimum, it is sensitive to outliers. Okay, since range is maximum minus minimum, it is sensitive to outliers. So what is a variance? A variance uses all the observation. It measures the average of the squared deviations from the mean. It measures the average of the squared deviations from the mean. So the derivations from the mean will be, deviations from the mean will be x minus x bar, x2 minus x bar, and xn minus x bar. So the population variance formula is summation I is equal to 1 to n x minus mu the whole square divided by capital N, where capital N is the population size, and sample variance is x square is equal to summation I is equal to 1 to n xi minus x bar by the whole square divided by n small n minus 1, where small n is the sample size. Okay, so effect of adding a constant, y1 is equal to x1 plus c for all I when the new variance is equal to old variance. So when you are adding a constant, new variance is also equal to old variance, and new standard deviation will be equal to old standard deviation. Okay, so the sample variance or the sample standard deviation, or the population variance or population standard deviation, will not change when we add or multiply, when we add a constant. Okay, This is for adding alone. When we add a constant, there will be no change in the variance or standard deviation. Okay. But when we multiply them by a constant, see, when we multiply them by a constant, new variance will be equal to k square into old variance, which means new standard deviation will be equal to k into old standard deviation. Okay, so new variance will be equal to k square into old variance, while new standard deviation will be equal to k into old variance. Sorry, old standard deviation. So standard deviation is just the square root of variation. So the population standard deviation will be the root of population variance, and sample standard deviation will be the root of sample variance. Okay. So sample deviation has the same unit as the original data. Okay. And now let us see what is a percentile and numerical summaries. Okay, so what is a percentile? The sample 100p percentile is the data value that has the property that at least 100 percentage p of the data are less than or equal to at least 100 into 1 minus p data of the data are greater than it. So p is equal to 0.5 means 50th percentile, which is the median. Okay, so we'll be having first percentile, 50th percentile and 99th percentile. So 99 percentage of the data should be less than this values. 1 percentage of data should be greater than this value, and 50 percentage of data should be in the middle of this value. Okay, so if two data values satisfy this condition, the percentile is the arithmetic average of those two values. Okay, so how do we compute a percentile? We are going to arrange the data in the increasing order, and we have to compute NP, where N is the number of observations. Okay, if NP is not an integer, we have to take the data at position. Not an integer means we have to take the data at position which is equal to smallest integer greater than or equal to NP. And if NP is an integer, the percentile will be equal to the average of the data at positions NP and NP plus 1. See here, we are having the original data like this, and we have to order the data like this. Okay, so 1 2 3 4 5 6 7 8 9 10, we are having 10. Okay, so the 0.1 percentile will be the NP is see here the P is 1, sorry, here the P is 0.1, P is 0.1 and N is 10. So the value is NP value is 1. Okay, NP value is 1. So here it is an integer, so we'll be taking the data at positions 1 and 1 plus 1 2. So 1 comma 2, you will be taking the average of the value at 1 comma 2. So which will be 35 plus 38 divided by 2, which is 36.5. Then you are having 0.25 percentile, which is 0.25 into 10. See, this is P value, this is N value. 0.25 into 10, which is 2.5. So it is not an integer. It is not an integer. So we will be taking the smallest integer. Sorry, the integer, smallest integer which will be greater than NP. The smallest integer which will be greater than NP is 3. Okay, the smallest integer that will be greater than NP will be 3. So I'm going to take the value at the third position. So the 25th percentile will be 48. Okay, and see the 50th percentile, 0.50 into 10, which will be 5. So 5 is the integer. So I have to take the average of the data at positions 5 and 5 plus 1 6. So 60 plus 66 divided by 60 plus 66 divided by 2, which will be 60 plus 66 divided by 2, which will be 126 divided by 2, which will be 63. Okay, so and 0.75 is 10 into 0.75, which is 7.50. So 7.50, and NP is not an integer, so I am to take the value at 7.5. We have to take a smallest integer which is greater than 7.5, that is 8. So I have to take the value at the 8th position, which is 68. Okay, then see here, I am going to have the 1 percentile, first 1th percentile, that is 1 into 10, which is equal to 10. Therefore I have my NP value is 10, which is an integer. So I have to take the average of the data at positions 10 and 10 plus 1, 11. I am not having the 11th position here. So I have to consider the value at the 10th position itself. So 82. So 82 is the maximum value. There is no 11th value. So 100th percentile is equal to the maximum value. Okay. So this the concept we just now saw is called as percentiles, and now we are moving to quartiles. Okay, now we are moving to quartiles and interquartile range. And Q1 is equal to 25th percentile, that is first quartile, that is lower quartile, and Q2 will be equal to 50th percentile, that is median, that is second quartile, and Q3 will be equal to 75th percentile, which is the third quartile, what we call as the upper quartile, and IQR, that is interquartile range, is equal to Q3 minus Q1, that is 75th percentile minus 50th percentile, that is 75th percentile minus 25th percentile, which is upper quartile minus lower quartile. Okay, so see here, so the 5-number summary will be including minimum value, Q1 value, that is 25th percentile, Q2 value, which is the 50th percentile, and Q3 value, which is the 75th percentile, and we'll be having the maximum value, which is the greatest value. Okay, so the distance between each these values will be 25 percentage. So from this data, from this example, this is the Q1 value, this is the Q2 value, and this is the Q3 value. Okay, Q1, Q2, Q3. So see here, Q1 is equal to 47, Q2 is equal to 63.5, and Q3 is equal to 68. So this is how we calculate. Okay, so summary of all the numerical summaries will be: range is maximum minus minimum, variance is average of all the square deviations, that is summation xi minus x bar the whole square divided by n minus 1. This is sample formula, and for population you will be having xi minus mu the whole square divided by n. Okay, and the sample standard deviation will be the root of sample variance, and the the population standard deviation will be the root of population variance. Okay, and the percentile will be calculating using this algorithm, that is if NP, we have to calculate NP, where when NP is not an integer, you have to take the data at the position with the value that take the data at the position whose value is the smallest integer greater than NP, and if NP is an integer, we have to take the percentile value as the average of the data at positions NP and NP plus 1. Okay, and for IQR, interquartile range will be Q3 minus Q1, where Q3 is the 75th percentile and Q1 is the 25th percentile. Okay, and range is very sensitive to outliers, while variance, standard deviation, percentile, and IQR are not related to outliers. Okay, this is what you have to remember. So this brings us to the end of this session. See, now we have saw part 1 of our best one shot statistics video in 2 parts. Part 2 will be released very soon, so stay tuned. The link to the next part will be available in the pinned comment and added to the playlist. If you found this revision session helpful and want to complete the qualifier preparation with live classes, one-to-one mentoring, 24/7 doubt support, structured practice, previous year paper discussion, and our newly launched qualifier crash course, call the number provided in the pinned comment or check the details in the description below. If this video helped you, don't forget to like, share, and subscribe to the channel so you never miss out our IIT Madras BS Qualifier content. Thank you for watching. Keep practicing, stay consistent, and I'll see you in part 2. Until then, all the very best for your IIT Madras BS Qualifier. Let's crack it together. Welcome to India's #1 and largest IITM student community with 70,000 plus students on board. If you are preparing for the IIT Madras BS degree qualifier, then you are in the right place because this is the best to one shot statistics video in 2 parts. This is the second part, enough to crack your qualifier statistics. In this revision series, we will be covering all the important statistics concepts, shortcuts, problem solving techniques, and exam oriented questions that you need for the qualifier. Whether you are revising at the last minute or strengthening your fundamentals, this series is designed to maximize your preparation. Before we begin, we are excited to announce that we have officially launched our IIT Madras BS Qualifier crash course. If you want structured preparation with expert guidance, this is the perfect opportunity to boost your qualifier score. Along with the crash course, if you are looking for one-to-one live class mentorship, 24/7 doubt support, strategy session, structured preparation, and previous year paper solving in live class, you can join India's #1 IIT Madras BS Qualifier coaching through the link provided in the pinned comment below. Our coaching program has consistently delivered 90 to 100% selection rates with top-notch faculty having a minimum of 10 years of industry experience. Our team owns 13 US patents in AI, ML, and IoT, and we also serve as guest lecturer at IIT where we teach advanced topics like LLM, RAG, and AI agents. So grab your notebook, stay focused till the very end. Let's begin the best one-shot statistics video in two parts, which this is the second part to help you crack your IIT Madras BS qualifier. Now let us continue our revision from where we left off. Now we have to revise only week 4. Okay, that is association between two variables. In this content we will understand the association between two variables. So where we stand now, we know what is a statistics, and there are two main branches in statistics which are descriptive and inferential, and our course focuses on descriptive statistics and lays foundation for inferential statistics by introducing probability. And we saw how we'll collect tablet and present data, and columns will represent variables and rows will represent cases, and how the data is classified categorical or numerical, like that. And we saw the discrete and continuous types, and we saw the scales of measurement as nominal as categorical, ordinal is also categorical, interval is numerical, and ratio is also numerical. Okay, so we saw what are all the arithmetic operations possible in all these four categories. Only mode is possible in nominal, while ordinal has a ordinal has median and mode, and interval data and ratio we can calculate all mean, median, and mode. And for describing categorical data, we were using frequency table and relative frequency, and graphically we used pie charts and bar charts, and for descriptive measures we used mode and median. And for describing numerical data, we used frequency tables and for single values and for grouped data. And the measures of central tendency we saw mean, median, and mode. And for measures of dispersion we saw range, variance, and standard deviation. And we also saw what are percentiles and interquartile range. And for graphical summaries we used histogram, stem, and leaf plot. Okay, so see here we saw also scales of measurements like nominal, ordinal, interval, and ratio. And the types of data for each scales are categorical. Nominal is categorical, ordinal is categorical, interval is numerical, and ratio is numerical. And if is ordering is possible, no, nominal cannot be ordered, but ordinal, interval, and ratio can be ordered. Okay, so the arithmetic operations which are possible in each scales of measurement is in nominal only counting is possible, and in ordinal also only counting is possible, and in interval you can do addition and subtraction, but in ratio you can perform addition, subtraction, multiplication, division, anything you want. Okay, so nominal and ordinal will come under categorical data, and interval and ratio will come under numerical data. Okay, and what should we know now? Now we know to categorize data as categorical or numerical, and we can identify the scale of measurement of a variable, and we can summarize a single variable using tables and using graphs. Okay, and we can compute appropriate descriptive measures like mean, median, mode, range, variance, standard deviation, percentiles, IQR, interquartile range as applicable to each question. Okay, and we are beware of good practices in presenting data, and we also know the area principle. So see here, now we are going to check the association between categorical variables. We want to know if two categorical variables are associated, that is related. Okay, so let us see one example first. Gender versus ownership of smartphone. So is ownership of a smartphone associated with the gender? So the variables given are gender, which is nominal. So the levels will be male and female. owns a smartphone, this is also nominal, where the levels will be yes or no. So the data collected is n is equal to 100 students, and ID will be 1 to 100, and the gender will be male, female, 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 like that, according to the gender. Okay, and owns phones will be yes or no, like this. So I'm going to draw a contingency table. See, I'm going to draw a contingency table like this. One factor is gender and the other factor is owning a smartphone, where the levels are female, male, and yes or no. So I'm drawing contingency table, and if we get female who owns a smartphone, we have to put the count here. And for females who do not own a smartphone, we will be putting their counts here. And the number of males who own a smartphone, we will be putting the count here. And the number of males who do not own a smartphone, we will be putting their count here. And we will be having the column total, and we will be having the row total, and we will be having the total of all the students. Okay, so the both variables are nominal, so the order does not matter. Okay, so see here, example 2, income which is ownership of smartphone, and is ownership of a smartphone associated with the income. Okay, see here, where the variables are income, which is ordinal, high, low, and medium. They can be ordered, right? High is greater than, medium is greater than low. And owns a smartphone, nominal, the levels are yes or no, they cannot be ordered. So you do not have to preserve the order for this one, owning a smartphone, but you have to preserve the order for this one. See, this contingency table is wrong because it is high, low, and medium. It should be high, medium, low, or low, medium, high. Okay, anything like that, but you should not collapse the order here. So this is how the contingency table for income versus ownership of smartphone will be. Okay, now we saw how do we construct a contingency table. Okay, a contingency table is used to compare two variables with more values. Okay, two variables with more levels, with more values. Okay, and let us see how do we organize a bivariate categorical data. So to organize a bivariate categorical data, we will be having a two-way table which is called as contingency table. So now we study the association between two categorical variables, and we summarize the data using a two-way contingency table where row represents the levels of variables 1, and column represents the levels of variable 2, and cell entries is the counts of each levels. And if both variables are nominal, the order does not matter. If one variable is ordinal, you have to preserve the order, and we will use the relative frequencies next to understand their association. Okay, so see the next lecture here, association between two categorical variables. So why do we look for association? Association is not equal to causation. We want to know if the information about one variable gives the information about another variable. Okay, we want to know if the information about one variable gives the information about another variable. So see the example question here, is ownership of a smartphone associated with gender or with income? This is the association we want to find. See, is ownership, the variable ownership of a smartphone is associated with gender or is it associated with the income? Okay, so we need to know how do we interpret relative frequencies. So row relative frequencies means compare across columns within a row for each gender. Okay, so row column relative frequencies means we have to compress across a row within a column. Okay, so see the example 1 here. The variables are gender versus ownership. Okay, so the variables will be gender, which is nominal, so the levels are male and female, and owns is not known, it is also nominal, so the levels are yes or no, and the number of students under study is 100. Okay, so the contingency table is like this. Now I have to calculate the row relative frequencies. That is, I have to calculate row relative frequencies like this. See, I have to add these two things and I have to calculate the row relative frequencies. So how do we calculate the row relative frequencies? Row relative frequencies for this column will be 34 divided by the row total 44. Okay, row relative frequencies means the rows observation divided by the total number of rows observation into 100. Okay, 34 divided by 44 into 100 will give us 77.27. Again, 10 divided by 44 will give us into 100 will give us 22.73 percentage. Similarly, 42 divided by 56 into 100 will give us 75 percentage, and 14 divided by 56 into 100 will give us 25 percentage. Okay. So this is how we calculate the row relative frequencies. See, you have to take that one particular value and that row total into 100. Okay. You have to divide these two values and multiply it with 100. And you have to divide these two values and multiply it with 100. Then again these two values you have to divide and multiply with 100. And then these two values you have to divide and it multiply with 100. And you have to represent it also in a contingency table like this. Okay. And the column relative values. So the column relative values will be like this. So this particular value divided by the column total 76 into 100. So again 10 divided by 24 into 100 will be see 34 divided by 76 into 100 will be 44.74. 10 divided by 24 into 100 will be 55.26. 42 divided by 76 into 100 will be 41.67. 14 divided by 24 into 100 will be 58.33 percentage. So this is how we calculate the column relative frequencies and row relative frequencies. So row and column relative frequencies are almost the same. So see, there is no much difference here. See here 75 77 there is no much difference. 22 25 there is no big differences. Similarly here also 44 41 55 58, so there is no much difference. So gender and ownership is not associated. Okay, there is no big differences in these two contingency table, so they are not associated. Now let us calculate the same for income versus ownership of the smartphone. See here, see, then what you will be doing, you will be first we will calculate the row relative frequency, then 18 divided by 20 into 100 which will be 90, 2 divided by 20 into 100 which will be 10, 39 divided by 66 into 100 which will be 59.09, 27 divided by 66 into 100 which will be 40.91 percentage. 5 divided by 14 into 100 which will be 35.71 percentage. 9 divided by 14 into 100 which will be 64.29 percentage. Okay, so this is the row relative frequency. Now we will compute the column relative frequency, which will be 18 divided by 62 into 100 will be 29.03. Okay, 29.03, and 39 divided by 62 into 100 will be 5.26. Okay, 5.26. So then you will be having 5 divided by 62 into 100, and then you will be doing the same process, and this is the column relative frequencies. Okay, this is the column relative frequency. See here, there are heavy differences between these values. See, heavy differences between these values, and see here also compare these three values, there are heavy differences, and also compare these two, we are having heavy differences. See, the row and column relative frequencies are different, so income and ownership are associated. Here we are not having much differences, so we concluded that gender and ownership are not associated, but here we are seeing some large differences, so we conclude that income and ownership are associated. Okay. And we will say that how we will visualize using the stacked bar chart, the same bar chart, the same process how we use a bar chart, but we have to stack the different categories above one another. This is what we call as the stacked bar chart. When we use just the counts, it will be called as stacked bar charts, and when we use the percentages we calculated in this row relative frequencies or in column related frequencies, it will be called as 100% bar chart. 100% stacked bar chart. That is, if we just use the frequencies from the contingency table, it is called as the stacked bar chart. Otherwise, if we are using the row relative frequencies or the column relative frequency percentages, then it will be called as the 100% stacked bar chart. Okay. Now, let's move on to finding the association between two numerical variables. So we already know that association is not equal to causation. We are not saying one causes the other, but now let us understand how do we find the association between two numerical variables. First, let us see what is a scatter plot. A scatter plot is a graph that displays pairs of values as points on a two-dimensional plane. A graph that displays the pairs of values as points on two-dimensional plane is called as a scatter plot. So it is used to explore the association between two numerical variables. It is used to explore the association between two numerical variables. So the explanatory variable will be on the x-axis and the response variable will be on the y-axis. In other words, the explanatory variable will be the independent variable and the response variable will be the dependent variable. Okay, so explanatory variable is the variable which is used to explain, and the response variable is the variable which we need to explain. Okay, so for example, see example 1 here, age versus height. So we are having some 5 persons and their respective ages and height. So see here which is the independent variable? Age. Height we call is a dependent variable because it will depend upon the height or depend upon the value of the age. For example, a baby who is 1 year old will not be more than 100 centimeter, right? So if someone has written age as 1 and the height as 100 centimeter, then it will be wrong, right? Then it will be wrong. See, first the age is first year. He's in the baby is in this first year, and if the age is 100, then the height is 100 centimeter, then it will be wrong. A baby cannot be 100 centimeter, right? So this example is wrong. So this example is wrong here. So since height is dependent on age, here age will be the explanatory variable, that is will be on the x-axis, and height is the response variable, so it will be placed on the y-axis. Okay. As age increases, height will also increase. So this is a positive association. We are plotting all these points, and this is the scatter plot. And we are plotting all the points, and we are getting a increasing trend, right? So as age increases, the height is also increasing, so there is a positive association. So we plotted the points as pairs, that is age comma height as points. Okay, and similarly we can also use size and price of homes. See, size, the price of homes will depend upon the size, right? So here size is the explanatory variable, so it goes in the x-axis, and price is the response variable, so it will goes in the y-axis. So this is how we plot a scatter plot. And see here, as the house size increases, the price will also increase. So there is a positive association here also. Okay, so let us see the visual test for association. So look at the pattern of the points. Do we see a trend? Here it is a clear upward trend, that is it is a positive association. As size increases, the price also increases. Okay, so but see this data set, there is no clear pattern and little or no association. So scatter plots helps us to quickly understand the nature of the association. Okay, you don't have to do much calculations. You can just draw a scatter plot to find the nature of association. Then you can later on do some calculations and find the more accurate value. Okay, so beyond visual, we can summarize the association like this. So we can draw a line like this. So a line like this, a straight line that describes the overall trend in the scatter plot. See, the line here is denoting the increasing trend, right? Increasing trend. So this line is used to summarize the association. Okay, and also you have also used correlation coefficient. Okay, now we shall see how do we calculate the correlation values. the next one. Okay, so how do we use the association between two variables? We will be using a scatter plot where x is the explanatory variable and y is the response variable. We look for pattern, not causations. Okay, so a scatter plot is a graph that displays pairs of values as points on a two-dimensional plane and is used to explore the association between two numerical variables. So there will be many patterns in the scatter plot. So it will depend upon the direction. So if it is going an upward trend, there will be a positive association, and downward trend. See, price versus age of the car. If the age of car increases, then price will decrease, right? So when one variable increase, the other variable decrease means that there is a negative association. Okay, negative trend. That is upward trend, downward trend. Okay, and if the pattern is linear, then the point follows a straight line pattern. Okay, and if the pattern is curved like this, then the points follow a curved pattern. Okay, then the points followed a curve pattern. So, and we can also see clustering in this. So when the data is tightly clustered, that is closely placed together like this, then there is less variation in the data. And if the data is more spread out, okay, and if the data is more spread out, then there is more variable, more spread in this data. That means the data has more variance. Okay, so you can understand these points also from the scatter plot. Okay, and you can also locate outliers from the scatter plot. See, all the data are concentrated here, but some 2 points is located here. So these are what we call as the outliers. Okay, from the data we can from the scatter plot, you can choose the explanatory variable and the response variable, and you can look for direction and whether they are linear or curved, and whether they are clustered, or they are tightly close together, or they are spread out. And we can also see outliers from the scatter plot. Okay, now let's move on to covariance and correlation, which are the measures of linear association. So now let us up to now we saw how do we find the association using a scatter plot. Now we are going to have some numerical measures to measure the association. Okay, so our goal is to, we have seen scatter plots to describe association. This is just a visualizing thing, right? But can we quantify the association? Can we have some values for association? Yes, we can have some values for association by using two popular measures called as covariance and correlation. Okay, so both measure the strength of the linear association only. For example, we are having the age and the height data. Okay, we are having the age and the height data. Let us have a plot for that. And now let us calculate the deviations from the mean. Okay, let us calculate the deviations from the mean. First let us calculate the mean for this one. 1 plus 2 plus 3 plus 4 plus 5 divided by 5, which is 15. Okay, and 15 divided by 5, which is 15 divided by 5, which is 5. Okay, sorry, 15 divided by 5, which is 3. So 15 divided by 5, which is 3. So our x bar is equal to 3. Okay, so 1 minus 3 will be minus 2, 2 minus 3 will be minus 1, 3 minus 3 will be 0, 4 minus 3 will be 1, 5 minus 3 will be 2. Okay, and then we'll also calculate the y bar, that is 75 plus 85 plus 94 plus 101 plus 108 divided by 5, which is 92.6. Okay, so 75 minus 92.6 is minus 17.6, 85 minus 92.6 is minus 7.6, 94 minus 92.6 will be 1.4, and 101 minus 92.6 will be 84, and 108 minus 92.6 will be 15.4. So then we will be calculating x minus x bar into y minus y bar, that is the product of these two columns. Okay, so minus 2 into minus 17.6 will be 35.2, and minus 1 into minus 7.6 will be 7.6, and 0 into 1.4 will be 0, 1 into 8.4 will be 8.4, and 2 into 15.4 will be 30.8. Okay, so we have to add all these things. We will be getting summation x into summation x minus x bar into y minus y bar will be 82. So see here, most products are positive means we will be having positive association. This is some assumption, but let's calculate the value too. Okay, so covariance quantifies the strength of the linear association. The formula for covariance is summation xi minus x bar into yi minus y bar divided by n, where n is the number of pairs. So for this example, we got the summation value was 82.0, right? So 82.0 and n is equal to 5. So covariance is equal to 82 divided by 5, which is 16.4. Okay, so how to interpret? If the covariance value is greater than 0, then we'll be having a positive linear association, and if the covariance value is less than 0, then we'll be having a negative linear association, and if the covariance value is equal to 0, then there will be no association. Then they are not, then the variables are not related. Okay, so this is how we calculate the covariance, and then we'll be using correlation. And the correlation standardize covariance to remove the effects of units. Okay, so covariance is also a measure for association, but correlation, see, we are getting values like 16s here, right? But correlation will come only between minus 1 and 1, minus 1 and 1. So the correlation standardize the value of covariance. Covariance will can have any number of values, like it can have 50, 60. It can have answers like this. Okay, but correlation standards covariance to measure them in one scale of measurement. See, the correlation values will be one between minus 1 and plus 1. Okay, will be between this interval minus 1 and plus 1. So the formula for correlation will be R is equal to covariance of x comma y divided by standard deviation of x into standard deviation of y, and the value for the correlation will be between this. The correlation will be denoted using R. So it will be minus 1 less than or equal to R less than or equal to 1. So if R is greater than 1, then there will be positive linear correlation. If R is less than 0, then there will be negative linear correlation. And if R is equal to 0, then there will be no linear correlation. And if R is greater than 1, there will be a strong positive correlation. And if R is close to minus 1, then there will be a strong negative correlation. Okay, a strong negative correlation. So this is what we call as a correlation matrix. Okay, correlation matrix. So this shows the correlation coefficient between every pair of numerical variables. So if you have to find the correlation between the same variables, you will be getting 1. So this is why the diagonals are always 1, and between these two variables you have to compute the correlation using this formula. Okay, so the diagonal entries are always be 1, and see, x2 to 1 and x1 to x2 will be same. Okay, so this one r12, this is also r12. Okay, so let us see how we interpret correlation and correlation matrix. And we know that correlation coefficient will be equal to covariance of x comma y divided by sx and sy, where sx xy means standard deviation of x and y. And equivalently, you can also expand this covariance formula like this. Okay, R is equal to summation I is equal to 1 to n xi minus x bar into yi minus y bar divided by root of xi minus xi minus x bar the whole square into root of yi minus y bar the whole square. Okay, so we have to remember covariance is equal to summation xi minus x bar into yi minus y bar divided by n, where sx is the standard deviation of x and sy is standard deviation of y, and r has no units as it will be it will be fitted into this range. There will be no unit. Okay, so there are two formulas for computing correlation. You can use anything you want. So how is R determined? R is determined using the sign of covariance. See, if in the quadrant 1, x1 minus x bar will be greater than 0, so the product will also be greater than 0. And in quadrant 2, xi minus x bar will be less than 0, while yi minus y bar will be greater than 0. So since one of the two terms is less than 0, the product will also be less than 0. Here, see, xi minus x bar is less than 0, it means negative, and yi minus y bar is also less than 0, which means it will also be negative. So product of two negative terms will turn positive. So product will be greater than 0. And see the Q4 here, xi minus x bar is greater than 0, quadrant 4, and yi minus y bar is less than 0. So one of the two values is less than 0. So the product will also be less than 0. So the covariance is the average of these products, and R has the same sign as covariance. So how do we interpret the value of R? If the R is equal to 1, then it is a perfect positive correlation. All the points will be on a straight line. And if R is between the range 0 to 1, it is a positive correlation. The point will trend up more, okay, as R gets smaller. If R is equal to 0, then there will be no association. Then the two variables are not related. Then the plot will be scattered here and there, okay. And if R is between -1 and 0, then there will be a negative correlation. So the points are scattered here and there while we are having a negative trend, okay. And if R is equal to -1, then you will be having a perfect negative correlation, that is all the points lie on a straight line in a downward trend, okay. So see the examples here. We are having same strength but different directions. See, if we are having R is equal to 0.80, then we will be having greater upward trend. Okay, strong positive linear association. And see here, R is equal to -8.0 means you will be having a strong negative, that is downward trend. And if R is equal to see here 8.0, so there some points are scattered here and there, and here also 8.0, some particles scattered here and there. But here see, it is close to 1. It is very close to 1, positive 1. So you will be having an upward trend where the points lie on the straight line, okay. And here it is a middle value, so positive middle value. So you will be having an increasing trend, but the data will be scattered here and there. And see here, it is very close to 0. It is very close to having no linear association. So it is a very weak positive value. So the data will be scattered very far away, okay. So the limitations are correlation captures only linear association. It may be 0 even if a curved relationship exists. So it is sensitive to outliers and it does not imply causation. R describes strength and direction, not the exact form of relationship. So the correlation describes the strength and direction, and it is not the exact form of relationship, okay. So remember this rule of thumb, okay. So if it is 0 to if the value is between 0 to 0.19, it is very weak. 0 to 0.2 to 0.39, it is weak. 0.4 to 0.59, it is moderate, and 0.6 to 0.79, it is strong. And if this 0.8 to 0.1 means it is very strong, okay. The same goes for negative. You can use this rule for both negative and positive values. So if it is positive means you will be using very weak positive. If it is negative means you will be using very weak negative. That's the only difference, okay. So let us see how we summarize a linear association with the line. Okay, so summarize a linear association with a line means, so if we draw a line and if all the points lie closely to that line, then we say that there is a strong positive association. So we conclude that the price of the house will strongly depend upon the size of the house, okay. So the price of the house will strongly depend upon the size of the house, as the upward trend line has the data points lying very closely to it. Okay, since the data points are lying very closely to the trend line, we can say that the prices of the house will positively depend upon the size of the house. Okay, so let us understand what does R square means. So R square is equal to the coefficient of determination determination which is equal to the proportion of variability in y that is explained by the linear relationship with x. So the that is r square is just the square of r. Okay, it's just the square of the correlation value. When sometimes r will have negative values, like correlation will have negative values. When we square that, r square will be always positive, right? So the range of r square will be 0 to 1. So when it is closer than 1, closer to 1, it is a better fit. If it is closer to 0, it is a poor fit. So r square does not tell us the direction. Only it will tell us whether it is a best fit or a poor fit. Okay. So this is the example for age versus a price of car. This is a negative trend. So negative trend means the see here, we are having a strong negative association. That is, if the age of the car increases, the price of the car will decrease. Okay. So they are having a negative relationship, and the correlation is equal to r is equal to minus 0.92. So we are having a strongly negative association between these two variables. Okay, so this is the example for no association. The data are very scattered away, and the line is also straight, and see the r is equal to 0.13, very weak. Okay, so slope is equal to 0, so no trend. R square is also close to 0, so we'll be having almost no variability. So this means that the variables are not associated. Okay, so this is how we interpret the examples, interpret the problems using the trend lines. Okay, now remember this. When we are given the value of r square, okay, see, if correlation r is positive 1, then r square will be 1, then it will be a perfect linear relationship. And if the r value is correlation value is 0.8, then r square will be 0.64. It is a strong positive correlation. And if r is 0, then r square will also be 0, then will be no linear association. And if the correlation value is minus 0.8, then r square will be 0.64, meaning there will be strong negative correlation. And if r is equal to minus 1, then r square will be 1, then will be a perfect linear relationship between those variables. Okay. So if you are given a slope of line, and if m is greater than 0, then you will be having a positive association. And if the slope is less than 0, then you will be having a negative association. And if m is equal to 0, that is the slope is equal to 0, you will be having no linear association. Okay. Now let's move on to association between a numerical variable and a categorical variable, that is dichotomous categorical variable, which means you will be comparing one numerical variable and one categorical variable. So far we saw how to compare two categorical variables and how do we compare two numerical variables. But now we are going to compare one numerical variable and one categorical variable. Okay, so the big idea is we want to study the association between one numerical variable and a categorical variable. So we have to find if gender affects the marks of the student. Okay, so in these terms we will be using a point biserial coefficient formula. Okay, point biserial coefficient formula. See, for example, the teacher's question is, a teacher wants to know if female students perform better than male students in her class. So she collects all the marks of the 20 students along with their gender. So the data table will be like this: student number, gender, and their marks. Okay, so gender is a categorical variable with two levels, female and male, and marks is a numerical variable that can take any value in the range 0 to 100. Right? So coding the categorical variable will be, to compute correlation, we must code the categorical variable numerically. See, to find the correlation, you want two numerical values. So you will be coding the gender like this: female as 1 and male as 0. So you will be coding females to 1 and males to 0. So this is what we call as coding the categorical variable. Then you will be scatter plot the two different scenarios. So marks out of 100, you will be drawing the marks of all the male students here like this, and we are drawing the marks of female students like this. test 1 you are having no clear association, and in test 2 you are having the values of females are performing better. Okay, so the male students are clustered together towards the low marks, while the female students are clustered together towards the higher marks. Okay, which means there is a positive association between gender and marks. So we cannot fit a meaningful line here. Since they are classified as two categories, you cannot fit a meaningful line here like this. So we use a formula called as point biserial correlation to summarize the association. So let x be the numerical variable and y be the dichotomous categorical variable, which is gender coded as 0 or 1. So you will be mostly coding the categorical variable as 0 or 1. So let n1 be the number of ones, that is females, and n not be the number of zeros, which is males, and n be the number of males plus females, which is 20. Okay, so x1 bar be the mean of x for y is equal to 1, that is mean of females. X0 be the mean of y for y is equal to 0, that is it is the mean of males. And sx will be the standard deviation of x for the whole sample. For the whole sample you will be calculating the standard deviation. Then you are using this formula RPB, that is point biserial correlation coefficient is equal to x1 bar minus x0 bar divided by sx root of n0 n1 divided by n square. So this RPB is equivalent to the line Pearson correlation coefficient between x and some coded y variable. Okay, so we have now we just generally saw how to do that. See, we have to code the categorical variable as female is equal to 1 or male is equal to 0. Then we have to compute the mean for y is equal to 1 and the mean for y is equal to 0. And we have to compute the standard deviation for all the observations. And n1 is the number of ones and n0 is the number of zeros. And we have to substitute all these values in this formula to get the point biserial correlation coefficient. So if the RPB value is greater than 0, then the group 1 has higher variance. If it is less than 0, then the group 0 has higher values, and if it is equal to 0, then there is no association between gender and the marks scored. So that brings us to the end of this session. This is the part 2 of our best one-shot statistics video in 2 parts. Part 2 was already released. So you can find the link of that part in the pinned comment below. If you found this revision session helpful and want to complete qualifier preparation with live classes, one-to-one mentoring, 24/7 doubt support, structured practice, previous year paper discussion, and our newly launched qualifier crash course, call the number provided in the pinned comment below. If you found this video helpful, don't forget to like, share and subscribe to the channel so you never miss our IIT Madras BS Qualifier content. Thank you for watching. Keep practicing, stay consistent, and I'll see you in the next video. Until then, all the very best for your IIT Madras BS Qualifier. Let's crack it together.